Thank you.
Thank you, Beshad. Hello, everyone. I'm Payman, a board member of STLE Toronto, and we are so happy to have Wilhelm today. Wilhelm Rabin is a graduate chemical engineer with more than 35 years of experience in formulation and maintenance of metalworking fluids and industrial lubricants. He worked for almost 23 years as a senior development chemist in the R&D department of a medium-sized lubricant manufacturer in southern Germany. During this time, he was in charge of the development of metalworking fluids and industrial lubricants. In 2011, he joined Lanxess Deutschland as a senior manager application technology. He is in charge of the development of guideline formulations and additive package of metalworking applications and of other research projects. So with no further ado, we pass the presentation to Wilhelm and enjoy. Thank you.
Great. So thank you very much for the kind introduction. And hello, good morning, good afternoon, good evening to everybody. First of all, I would like to introduce Lanxess quite briefly and also the business unit Lubricant Additives. Lanxess, as most of you may know, is a special chemicals company, and its headquarters is based in Germany, in Cologne. The business unit Lubricant Additives, which is a part of the Lanxess company, offers a broad portfolio of components for lubricants, including synthetic base stocks and intermediates like high viscose polyalpha olefins, special synthetic esters and diphenylamine, but also lubricant additives like antioxidants, detergents, extreme pressure and anti-wear additives, corrosion inhibitors, and also additive packages for industrial lubricants, for metalworking fluids, for greases. And additionally, it also offers synthetic industrial fluids, finished fluids for aviation, fire-resistant hydraulic fluids, and special calcium sulfonate complex greases. All these premium products are meeting the highest standards, and there's also an excellent technical support for customers. So the plan of Lanxess as an entire company is to become climate neutral in its Scope 1 and Scope 2 emissions until 2040. Actually, these emissions have already been reduced by more than 60% compared to 2004. And it is also planned to reduce the Scope 3 emissions continuously and to become net zero in it by 2050. So far for the introduction, I will now go to my first presentation, which has the title Rust Preventives based on water as solvent, challenges and advantages. And I will start with an explanation of the importance of corrosion protection, and then I will compare the advantages and disadvantages of using organic solvents or just water as a solvent for rust preventives. And this is followed by a description of the application procedures of both types of RPs. And I will also show the test results of an emulsifiable water-based corrosion inhibitor. Finally, I will come to a summary. Corrosion protection is a quite important topic because corrosion actually generates more damage than fatigue. And there's a study from 2016 that estimates the annual global costs of corrosion at approximately 2.5 trillion US dollar, which is approximately 3.4% of the global gross domestic product. And according to another study, the direct costs of damage caused by corrosion just in the US were 276 billion US dollars in 2006. And these are only the direct costs. Indirect costs, like loss of productivity, downtime of production facilities, and so on, they are at least as high as the direct costs. So within the last 3 to 4 decades, supply chains became more complex and transport routes became longer and transport volumes increased drastically. And particularly for the manufacturing industry, the corrosion during transport or storage of semi-finished parts like bars, slugs, or blanks, and of finished parts, it has become a real challenge because the corrosion occurs due to bad weather conditions or changing climates during overland transport, but also by seawater impact during maritime transportation or just by high humidity storage conditions. And the temporary corrosion protection of parts during transportation or storage is the typical application of rust preventives. Many rust preventives were in the past and are still based on organic solvents. This technique is quite common since long times. Advantages are, the application of this kind of rust preventives is just a very established process. Drying times are usually short. After removal, the rust preventives are very easy to dispose. They can just be burned. And the formulations are not very complex. But these organic solvents, like white spirits, are volatile organic compounds, so-called VOCs. So they act as a greenhouse gas and contribute to global warming. In reaction with nitric oxides and sunlight, they form ground-level ozone, which is a harmful air pollutant. And many VOCs are harmful by themselves and can cause health issues for the workers. So there are already restrictions for the use or the emission of VOCs in many countries, like in the US, in Canada, in the European Union, Australia, or Japan. So it's necessary to install an exhaust gas treatment like an afterburning system to eliminate the emitted solvent vapors. Furthermore, this kind of rust preventives are highly flammable because of the flash point of the organic solvent, and they usually have a high water pollution classification, which requires additionally safety measures for transport and storage. But what if just using water as a solvent? There would be no VOC release because there are simply no volatile organic compounds in the formulation, and therefore there's also no exhaust gas treatment necessary. The formulations, the rust preventative, would be not flammable, and usually it would have a lower water pollution class. The quantity of material that needs to be transported or stored is also lower because 70 to 80% of the finished rust preventive is just water, which is usually available in every manufacturing site. And the disposal is still as easy as for other used lubricants. On the other hand, drying times might be longer, and because it's a new technology, some changes might be necessary in the application process. This chart is a comparison of the application procedures of solvent-based or water-based rust preventives. And it's including all the steps from the manufacturing of the part to the cleaning process, the application of the rust preventive, the transport and storage stage, and the removal of the rust preventive for assembling the part. And as you can see, for the solvent-based technology, there's always an exhaust gas treatment necessary during the cleaning of the parts, the application of the rust preventive, and also when the RP dries on the surface of the parts. With a water-based rust preventive technology, there is no need for an exhaust gas treatment because the only substance that evaporates is water. On the other hand, warming up the parts accelerates the drying process. The following test results were achieved with a water-based emulsion of a corrosion inhibitor package that we emulsified in a concentration of 10 or 20% in water. So these are the test results of a comparative study by using the salt spray test according to ASTM B117 on deep drawing steel sheets of deep drawing quality. The first line shows the test results of a standard oil-based rust preventive containing 10% of a corrosion inhibitor and 90% of a group 1 mineral oil. And the lines below show the test results of the emulsifiable corrosion inhibitor in combination with a group 1 mineral oil or group 2 mineral oil, naphthenic oil, or TMP3 oleate. And all these formulations were diluted in water. And as you can see, the anti-corrosion performance of these water-based emulsions is at least on the same level than the oil-based rust preventive. Additionally, we tested the emulsifiable corrosion inhibitor in a condensation climate with alternating humidity and air temperature. In this test, which is according to ISO 6270-2, one cycle consists on 8 hours at 40 degrees Celsius and 100% relative humidity. And this is followed by 16 hours at ambient temperature and ambient humidity. So one cycle is finally 1 day. And that test was stopped when the surface of the steel sheets was covered with corrosion at a level of 5%. And as you can see, the emulsion of 10% corrosion inhibitor, 10% mineral oil, after drying, it lasted on the steel sheets for 178 cycles or days until the corrosion limit of 5% was reached. And with 10% corrosion inhibitor and 20% mineral oil, it took even 220 days until the test was stopped. Of course, excuse me, just a moment, please. Of course, the drying time of water is longer than the drying time of organic solvents that have a low flash point. However, we compared the drying time of solvent-based rust preventives with the drying time of the rust preventive emulsion that also contains some secatives. And compared to a solvent-based rust preventive with a flash point of 40 degrees, this is the black line. The drying time of the water-based rust preventive, the red line, was a little bit, or was, let's say, significantly longer. But on the other hand, there is the low flash point of the rust preventive, which causes a danger of ignition, just 40 degrees Celsius. But if we compare the water-based rust preventive with one that is based on solvent, which has a flash point of 80 degrees Celsius, the water-based formulation dries much faster. After the application of the rust preventive, it's also important that the dried film can be easily removed by suitable cleaners. And therefore, we tested how easy or how difficult the film can be removed by two different types of water-based cleaners. One was a cleaner according to the industrial standard VDA 230-201, and the other one was a commercially available industrial cleaner for ferrous metals. So the sheet, which are covered with a dry rust preventive film, were dipped for 3 minutes in the different cleaner solutions. They had a temperature of 60 degrees Celsius. After that, we rinsed them with tap water for 30 seconds. And for better verification of the cleaning test result, we conditioned the clean steel plates by dipping them into a copper sulfide solution. So all the parts on the surface, all the surface areas on the steel sheets, which were perfectly clean, were then covered with a thin copper coating. And as you can see here on these photos, with both rust preventive formulations containing of 10% corrosion inhibitor and 10 respectively 20% of mineral oil and 80 respectively 70% of water, with a VDA standard cleaner as well as with a conventional cleaner for ferrous metals. The results were excellent, and the surface area on the steel sheets, the clean surface area was 100%. So the summary and conclusion for the first presentation just says that rust preventives based on water can, in our opinion, be a great alternative to meet today's environmental requirements. The new emulsifiable corrosion inhibitor technology offers excellent performance for long-term temporary corrosion protection. There are no emissions of VOCs, and the formulation, it also works without heavy metals like barium. The formulated rust preventive is not flammable because of its high water content. And the salt spray protection and the condensation alternating climate protection times are comparable to oil-based rust preventives. We also found that the stability of the prepared emulsion is excellent even at high water hardness. And finally, as I could demonstrate, the film, the protective film of this water-based cleaner is easily to remove by suitable water-based cleaners. There's a question.
I don't see any in the chat, but I have two questions if you want to address it now or wait till everything is finished.
We can also, I can try to answer it now.
Yeah, so two things. Number one, can you comment on the quality of the water that should be used for these kind of additives? And then do you recommend this kind of water-based rust protection to be used for the ocean shipment or sea shipment of the parts from like China to US or Canada?
First of all, regarding the water quality, we just used tap water to prepare the emulsion, and we also made tests with tap water with higher water hardness of about, as far as I remember, 200 ppm calcium. So the emulsion remained stable even with this higher water hardness. And regarding overseas transport, this is always depending on the thickness of the rust preventive film on the parts that have to be protected. But we found that the rust protection performance, for example, in the salt spray test, was absolutely comparable to other types of, let's say, commercially available rust preventive that are used for overseas transport.
Okay, thank you. There is no other questions in the chat, so if you want to continue, please go ahead.
Yeah, sure. I will now come to my second presentation. And the title of the second presentation is EP Additives with Improved Sustainability for Heavy Duty Metalworking Processes. So completely different, but I think both topics are somehow related to metalworking. I will now start with a general introduction into the function of EP additives, and this is followed by some detailed information about sulfur carriers and a comparison of the technical and the health and safety aspects of sulfur carriers and chlorinated paraffins, with which both work as EP additives for metalworking fluids. And in the second part of the presentation, I will show tribological test results of EP additive containing neat oil metalworking fluid formulations, as well as of waterborne formulations. And finally, I will again come to a summary and to conclusions. So chlorinated paraffins and sulfur carriers are both EP additives that are used in lubricants and metalworking fluids quite commonly to prevent adhesive wear, which is also called galling or cold welding. But how do EP additives work? So according to the common theory, in a first step, they physically adsorb on metal surfaces with their polar centers. And by this, they are already forming a kind of friction reducing layer. And with increased mechanical stress, that is usually followed by thermal stress, they chemically react with the metal surfaces, forming protective layers that are less shear stable than the metal structure itself. And by this, they prevent the metal surfaces from galling or cold welding. Sulfurized esters and triglycerides undergo a kind of intermediate step of so-called chemisorption, in which they also work as lubricity and anti-wear additives. So what are sulfur carriers? Now, sulfur carriers are sulfur-containing organic compounds made from unsaturated raw materials like olefins or unsaturated natural oils or synthetic esters. And they contain 2 to 5 sulfur atoms, forming a kind of connection or chain or bridge between the olefin or ester parts of the molecules. They have polar centers, as I already showed on the previous slide. And with these polar centers, which can be oxygen atoms or the sulfur atoms itself, with these polar centers, they can physically adsorb on metal surfaces. And by this, they make sulfur oil soluble and able to form protective layers, which protect metal surfaces from adhesive wear or galling. So they work perfectly as EP additives in metalworking processes and are excellent replacements for chlorinated paraffins. And this is how sulfur carriers are produced. So raw materials for the sulfurization process are vegetable oils like soybean, canola, or sunflower, respectively their methyl esters, but also animal fats or oils like beef tallow or lard can be used, or olefins from crude oil refining are also suitable raw materials for the sulfur carriers. And in a reaction vessel, sulfur and H2S are added, as well as catalysts and stabilizers, and the reaction products are sulfur carriers of light color and low order. Can you still see my presentation?
Well, I got one comment from Yusuf that he cannot, but I can. Everybody can see the presentation? Ayman, do you see that? Yeah,
Okay,
okay.
great.
Okay, cool.
Okay, so I can continue. So I will now come to a comparison of the technical aspects of chlorinated paraffins and sulfur carriers. And chlorinated paraffins are definitely effective EP additives at low machining speeds. But at higher machining speeds that are usually associated with higher temperatures at tool and workpiece, they tend to decompose, forming a hydrogen chloride, which has a strong negative effect on the tool wear. And in presence of water or moisture, chlorinated paraffins tend to hydrolyze, forming hydrochloric acid that can corrode the tool, the workpiece, and the entire machine tool. They are compatible with most other types of metalworking fluid additives, and they are colorless and odorless. And they are available at low costs, but in some regions, they have to be disposed by a high temperature incineration process to prevent the formation of toxic dioxins. And that makes the disposal quite expensive and also energy consuming. Sulfur carriers, on the other hand, they are available with different sulfur content, different activities, different polarities or molecular structures, so they can be easily adapted to the specific requirements of a single metalworking process. And they show outstanding efficiency over a broad temperature range from slow to high-speed machining processes. Their performance can even be increased by synergistic combinations with additives like over-based sulfonates, polycarboxylates, or some anti-wear additives. And they even support fast chip breaking in cutting processes because they make the chip surface more brittle and easier to break. They are also compatible with most other metalworking fluid additives, and most of them nowadays are of light color and low order. And they can be disposed by standard waste oil treatment, so there are no additional requirements on the disposal. Coming to the health and safety aspects, the short-chain chlorinated paraffins are already banned in many countries because they are persistent in the environment, they are bioaccumulative, and suspected to cause cancer. And there are intentions to ban or restrict the use of medium-chain chlorinated paraffins, the so-called MCCPs, for example, by the European Chemical Agency, the Japanese and South Korean Ministries of Environment, and by the United Nations Environment Programme, the so-called Stockholm Convention. As far as we understand, there have also been discussions about a ban of medium and long chain chlorinated paraffins in the United States. And according to our information, these discussions are still ongoing. Finally, chlorinated paraffins are categorized according to the globally harmonized system of classification and labeling of chemicals as very toxic to aquatic life with long-lasting effects. Sulfur carriers, on the other hand, they do not show any kind of hazard classification, and many sulfur carriers are based on renewable raw materials like vegetable oils. Some are already 100% biodegradable and absolutely non-toxic to aquatic organisms. They are even suitable for the formulation of lubricants that meet the requirements of the European Union Eco-label and the US Vessel Incidental Discharge Act, the former VGP. So many sulfur carriers can be certified as having low or no impact on the environment and showing no health hazards. Now I will come to some tribological test results, first with the neat oil formulations. And we use the tapping torque test to evaluate the performance of the different EP additives. This test uses a real thread cutting or thread forming process in which the torque is recorded and used for the evaluation of the different metalworking fluid formulations. And it can be done with many different workpiece materials and also different tools. The test results are very good transferable to other cutting or forming processes. So the torque is recorded and used for the evaluation of the tested formulations. That means a lower torque indicates a lower energy consumption in the process, and also it results in lower tool wear. I would like to start with our thread cutting test results, and we used parameter like the diameter of the core holes was always 3.3 millimeter. We used an M4 thread cutting tool. The depth of the thread was 6 millimeter. The speed was 800 RPM, and we always used the Group 1 ISO VTG 46 base oil for our tests. So first of all, we did the thread cutting in AISI 316 stainless steel, because contrary to normal steel, the surface of stainless steel is nearly completely covered with metal oxides, which makes it quite difficult for EP additives to interact with this surface. And it's also difficult for metalworking fluid to perform well with stainless steels. And we first used a non-coated tool for the thread cutting process. So we started with running the test with different sulfurized triglycerides with similar chemical structure and similar viscosity to evaluate the influence of the sulfur content and the sulfur activity, which is actually quite high. As you can see, with 10% of the inactive sulfurized triglyceride, adhesion, respectively cold welding, was detected at a depth of approximately 3.5 millimeters. With 10% of a medium active sulfurized triglyceride with nearly the same kinematic viscosity, torque was lower, but there was still a tendency for material adhesion towards the end of the cut. And only with the active sulfurized triglyceride, the cut was performed without any adhesion effect and with a comparatively low torque. Because the highly active sulfurized triglyceride showed the lowest torque, we additionally tested a sulfurized ester with almost similar sulfur content but lower kinematic viscosity. And as you can see, in this test with stainless steel, there was no significant difference. But we also tested a formulation containing 10% of a medium chain chlorinated paraffin, which contained 50% of chlorine. And when we compare the torque of the chlorinated paraffin containing formulation with the sulfur-based EP additives, we see that the average torque is quite similar. But the torque curves of the sulfur carriers are smoother and with less peaks in the records than for the chlorinated paraffin. Additionally, we tested thread cutting in stainless steel with a titanium nitride coated cutting tool, because this kind of cutting tools are often used for cutting tough steels. And we see that the average torque of the 10% sulfurized triglyceride formulation remains more or less on the same level as with a non-coated tool. However, the curve becomes a little bit more uneven. And when running the test with the 10% of the active sulfurized ester, the torque was actually slightly higher. But with 10% of the medium chain chlorinated paraffin, we can say that the torque was significantly higher, and there were also clear effects of adhesion visible at the end of the cutting process. So we can conclude that the chlorinated paraffin had a negative influence in this test series with a titanium nitride coated tool. Additionally, we did some thread forming tests. In thread forming, the internal structure of the metal is not destroyed, not cutted, but just deformed. So the material is compressed to the walls of the thread. Therefore, there are also no chips produced. Formed threads typically have a higher fatigue strength and are more durable than threads produced by cutting. In this test series, the core hole diameter was 3.7 millimeter. It was also an M4 cutting tool, but it was titanium aluminum nitride coated. The depth of the thread was 8 millimeter. The machining speed, again, 800 RPM, and we used the same base oil than for the thread cutting tests. So again, we started with stainless steel and with a 10% medium chain chlorinated paraffin formulation. And compared with this formulation, the formulation containing 10% sulfurized ester showed a slightly lower average torque, but a higher maximum torque. And this is probably caused by the lower viscosity and the lower lubricity of the sulfurized ester. But then we run the test with 10% of the active sulfurized triglyceride, and due to the higher polarity of its molecular structure, the torque of the active sulfurized triglyceride was significantly lower and also much lower than for the chlorinated paraffin. We did the thread forming also in S960QL high strength steel. The yield strength and the tensile strength of S960QL are similar to ultra high strength steels that are commonly used in the car industry. So therefore they are quite difficult to machine by forming processes. And in this, when running the test with this steel, the medium chain chlorinated paraffin showed a comparatively high torque, and the curve, as you can see, is quite uneven. With the sulfurized ester, and even more with the sulfurized triglyceride, same treat rate, the torques are much lower, which means that the forming process will be less energy consuming and also cause lower tool wear. But because the tapping torque test does not give a direct indication about tool wear, we therefore additionally used the 4-ball wear test to evaluate the influence of the EP additives on wear in this kind of mixed lubrication regime. And we run the test with the standard, which is ball bearing steel. as well as with stainless steel balls. And the test parameters, test conditions were according to ASTM D4172B, but also according to DIN 51350-3. When running the test according to the DIN standard, we found the lowest wear scar diameter on bearing steel with the inactive sulfurized triglyceride, which is 0.72. With the more active sulfur carriers, the wear scar diameter was slightly higher, larger. With stainless steel, oh, sorry, that was too fast. With stainless steel, the gray bars, the effect was reversed. So the wear was reduced with increasing sulfur and active sulfur concentration. But in any case, the wear was significantly lower when compared to 10% or even to 20% medium chain chlorinated paraffin. And when the test was done by using ASTM D4172 parameters, the active sulfurized ester showed high wear on stainless steel balls, probably due to its lower lubricity properties, but the sulfurized triglycerides again showed very low wear on bearing steel and also on stainless steel, particularly again when compared to 10 or 20% chlorinated paraffin containing formulations. But EP additives are not only commonly used in neat oil formulations, but are also important components for metalworking fluid emulsions that are used for heavy-duty metalworking processes. And yeah, all these different sulfur carriers, they can be quite easily emulsified and used as EP additives in soluble oils in semi-synthetic emulsifiable metalworking fluid formulations. For the evaluation of the performance of metalworking fluid emulsions, we used the so-called Reichert wear test. In this test, a steel cylinder is pressed against a rotating steel ring with a pressing force of 300 Newton. And during the test, the ring rotates in a container that is filled with a metalworking fluid emulsion. So there is a continuous supply of metalworking fluid to the contact zone. We can say this test simulates the tribological conditions of a turning process. Evaluation parameters are the travel distance of the noise generation. You can hear the noise very strong at the beginning of the test, and then after some time or some distance, the noise becomes much lower. And this point indicates the formation of a protective EP film on the metal surface. So a shorter noise meter are the better value. And also the size of the wear scar area on the cylinder after the tests are used for the evaluation of the different additives. And again, of course, a smaller wear scar area is the better result. This is just the guideline formulation of the emulsifiable semi-synthetic metalworking fluid concentrates that we used, containing naphthenic oil. And all the EP additives were added with a treat rate of 10% to this emulsion concentrates. So these are the test results, and compared to an emulsion without EP additives, there's a clear reduction of the wear scar diameters, the red bars, and also the noise meters when adding 10% of a sulfur-based EP additives to the emulsion concentrates. And with increasing sulfur content and activity, the duration of the noise generation becomes shorter. You can see this if you compare the sulfurized triglyceride with 10% sulfur content with the other triglycerides containing 15 or 18% sulfur. So this is a clear indication for faster formation of the protective EP layer. And compared to a long-chain chlorinated paraffin that we tested as well, the performance of the sulfurized triglycerides, the active ones, is significantly better. So finally, we can conclude that this presentation demonstrates that it is possible to formulate neat oil and also water-miscible emulsifiable metalworking fluids with excellent performance by using EP additives based on sulfurized renewable raw materials like vegetable oils or vegetable oil methyl esters. All the sulfur carriers that I showed in this test can be certified as based on renewable raw materials for more than 50%. The remaining percentage is just sulfur. They have a quite low impact on the environment. They are not labeled as hazardous to humans or to the environment, and they actually meet the requirements of the so-called LUSC list for environmental acceptable lubricants. I think the tribological test results show that sulfur carriers with the improved sustainability can even exceed the performance of conventional EP additives like chlorinated paraffins, even when machining high-strength steel or stainless steels. So thank you very much for your kind attention. Now I will try to answer your questions.
Okay, thank you very much, Wilhelm. So people in the room, if you want to unmute and ask your questions, please do so. Can I ask a couple of questions till other people type or ask their questions? Yeah, Wilhelm, are you okay?
Sure.
So is there, I think there is a difference between the activation temperature of these kind of different type of EP additives. Do you have any comment on that?
Yes, we know that there are charts showing different activation temperatures of chlorinated paraffins or sulfur carriers, but if you let's say have a look on common theories, the spot temperatures in metalworking processes are estimated as to be between 700 or 800 degrees Celsius. So in any case, these temperatures are high enough to make any kind of EP additive reactive. And I think also our test results show that under the conditions that we used and that are quite comparable to the conditions of common metalworking processes, the sulfur carriers work at least with the same efficiency than chlorinated paraffins.
Mm-hmm. Okay, cool. Thanks. The other question that I have is when we use group 1 to formulate these kind of metalworking lubricants, the sulfur content of that group 1, does it work like a EP additive or that's not relative?
It's not relative. The sulfur content was quite low, so we used relatively highly refined group 1 base oil with 0.2, I'm not really sure, 0.2, 0.3% sulfur in it. And when we tried to run a thread cutting test with the pure base oil, it was just not possible. It always came to a rupture of the tool.
Okay. And price-wise, a formulation with chlorinated paraffin versus a formulation with sulfur, do you see any increase or the same or decrease?
We usually saw a decrease of the torque in the thread cutting and thread forming processes, or at least it was similar, but in many cases it was even lower, the torque. And also the wear in the four-ball test was always significantly lower when running the test with the sulfurized esters or triglycerides. And it's also important to mention that the environmental the environmental acceptance of the sulfur carriers is much higher than for the chlorinated paraffins.
Yeah, but I mean for the pricing, the price of formulation, which one will be lower, or is there a cost saving associated to this switch from chlorinated paraffin to sulfur or no?
I think in this test that we did, we didn't had a look on cost savings. I suppose there will not be a cost saving for the formulation itself. There might be a cost saving in tool consumption or in time for changing the tool on the machine tool. But for detailed information about prices, I'm just the technical guy. I'm
I
sorry.
see. Okay. Sorry. Sorry, that's okay. So we have a couple of questions in the chat. What is the role of base oil viscosity in metalworking fluid cutting operation?
In metal cutting operations, usually the base oil viscosity is relatively low in most processes. It's finally depending on the severeness of the process. So for simple turning, drilling, or milling processes, or even for thread cutting, there's a viscosity usually chosen between, let's say, 22 and 46 centistokes. For grinding processes, it's usually often even lower. On the other hand, for heavy-duty cutting processes, like broaching, the viscosity is much higher. And in general, for most metal forming processes, the viscosity of the base oil is significantly higher than for cutting processes.
Okay, thank you. The next question is the chemistry question. Yusuf asks, sulfurized fat is made from adding H2SO4 plus fatty acid? Is it true?
Sulfurized fat is, just a moment. So a sulfurized fat, a light-colored sulfur carrier based on sulfurized fat is based on vegetable oil or animal oil and sulfur and H2S.
Okay.
Both is necessary to produce a light-colored, low-order sulfur carrier.
And I think the next sentence is, I don't know, it's a question or comment. Sulfurized ester can be mono or polyol ester?
Yes, can be both, of course.
Can be both. Okay.
Yeah.
And then I have a question myself. This ring and cylinder test, the Reicher test that you showed,
Yes.
Can you share the detail of the apparatus and the procedure with us or no?
Yes, in principle, yeah, I'm sorry. This is a test which is maybe quite commonly used in Europe, but not in the Americas. But this is a test that we often use to show EP properties of water mixed or waterborne metalworking fluids. So in principle, a steel cylinder, which is made of AISI 52100, so ball bearing steel, is pressed against a rotating ring. And the duration of the test is just the ring rotates for a length of 100 meters. So it's not measured by time, but by the rotated surface in meter. And after the end of the test, after the 100 meter, the cylinder and the ring are dismantled, and there is a wear scar on the cylinder. And this wear scar is just measured, the area is measured, and as smaller the area of the wear scar, of course, as better is the performance of the lubricant emulsion. So in that case, it's quite similar to a four-ball wear test, where also the area or the diameter of the wear scars is measured.
Okay, thank you. So let me see. Is there any question? No, I don't have any question in the chat. In the room, anybody has any questions that want to ask Wilhelm? Okay, Wilhelm, do you have any comments, anything to add to the end of your presentation before we conclude the meeting?
Oh, I just want to say thank you for your kind attention and your questions. And if you have some additional questions later on, you can, of course, contact me or also contact my colleagues from technical sales, from sales all over the world. So thank you very much.
How they can contact you directly, Wilhelm? Do you want to show and share your email address, or how should we contact you?
Yes. I cannot show my email address now, but it's in our conversation in our emails. So maybe you can send it later on.
Yeah, I can put it in the body of the email when I share the information with the team. Let me see, somebody. Okay, yeah. So we have Jordan contact information in the chat. So that should be good enough. Good. So Wilhelm, on behalf of, thank you. On behalf of the ST Toronto section board of directors, I want to thank you for your time and the interesting and great presentation that you delivered right now. And I thank everybody for joining us, and that would conclude this meeting. Have a great day and see you later.
Thank you very much. Have a